Hello all. In this video we're going to take a look at functions in OpenCV that allow us to make threshold images, to do various different kinds of thresholding on images. And as I said before, as a lead into this, I am going to talk mostly about the threshold function and the in-range function. And then I'm going to mention two other functions that are also kind of cool and do some interesting things, but that you might not need quite as much as the primary two. So let's take a look at the ideas here first. So thresholding an image, what does that mean? When we apply a threshold function, what does it do? It takes in an image and maybe some optional arguments that tell us exactly what we want it to do, and it produces a new image. Very often, that new image is black and white. So it's something that we could use as a mask if we wanted to, but we don't have to use it as a mask. We could instead just use that black and white image and do additional computer vision processing on it to, say, locate interesting objects in the image and so forth. How is it that it creates that black and white image? Well, it applies a threshold. So let's say we have a grayscale image and we say, I want you to separate the pixels into those that are above a threshold and those are below. So I'll set the threshold at 100. Any pixel that is brighter than 100 gets treated in one way. Any pixel that's less than 100 gets treated in another. The basic threshold function and the adaptive threshold, and to some extent the last one we're going to talk about, the back projection, all of those do something similar. They have a threshold point of some kind. The one exception we're going to look at is one that operates on color images, and there we're setting upper and lower bounds. So we're saying the first channel has to have at least this value and at most this value, and the second channel has to have at least this and at most this. Third channel has to have at least this and at most this. We can specify different ranges for each channel. And the only pixels we'll end up seeing as white are those that are all three channels fit within the range that we've specified. So these are some powerful tools. They can do many different things. And if you look at the functions, you'll notice that many times they take a lot of different inputs because they are meant to be flexible. You can change how they behave by changing up the inputs. So the main one we're going to focus on is this threshold function right away. We'll look at another later. It has four main inputs. It takes in the image that you want to manipulate. It takes in the threshold value. That's the value above where we make the separation between brighter pixels, pixels with higher values, and pixels with lower values. It takes in a maximum value. So for some of the modes that it operates in, the maximum value is what you set the pixels to if they are over the threshold. And then it takes in a mode. And the mode is where things get freaky because there are a lot of modes and they all do thresholding, but they do different kinds of thresholds. I'm actually going to switch over to the reading here. Well, I'll just end this by saying, yes, we are returned a new image. So it takes an image, makes a new one, which is the result of applying the threshold rules to the image that we've passed in. I want to go back and look at the reading here. So what we have here in the reading is a listing of the 5 most commonly used threshold modes. There are additional ones. We'll take a quick look at a couple of others, but these are the ones that most people use. And honestly, the most common one that I've ever used is this binary threshold. All right, so binary threshold, I have to move this down a little bit so that you can read all the text. There we go. The binary threshold, you have this threshold value. Anything above the threshold gets set to max val. Anything below the threshold gets set to 0. Binary inverse flips that around. Values over the threshold go to 0. Values under the threshold go to the maximum value. Truncate, it just chops off the top. So anything that goes over the threshold gets set to the threshold. And things under the threshold are left alone. To 0, any value above the threshold stays as it is. It's left alone. And anything below the threshold goes to 0. And to 0 inverse flips that around. So things that are above the threshold go to 0, things that are below the threshold are left unchanged. It's a little hard to picture exactly what's going to happen here. So the code in the reading, let me flip over to look at it. The code in the reading has a little program, and what I've done is I've just made a list here, thresh modes, that has those 5 thresh modes in it. So the binary, binary inverse, truncate to 0, and to 0 inverse. And then I wrote a little loop that will just display that result. And that's what we're going to look at and run right now. All right, so let's switch over to the desktop and we'll run this code and see what it does. All right, I want to move the output picture over here to the right so you can kind of see the code right here in the middle, and over here on the left you can maybe see and maybe possibly read the threshold descriptions themselves. This is thresh binary. So I gave it a threshold value of 128. So it's just basically anything that's in the upper half of brightness is been turned to white, and anything that is in the lower half of brightness has been turned to black. And we get this nice black and white image. If you were trying to identify the locations of the coins in this picture, this is looking pretty good. This looks like a pretty good way to identify coins. Let's try some of the other threshold modes. So binary inverse is just the opposite. It's white everywhere the previous one was black. It's black everywhere the previous one was white. It still looks pretty good. All right, this next one is the truncate. So this is, again, I'm keeping the threshold fixed at 128. Any pixel value over 128 is set to 128. And any pixel value below that, the darker pixels, are kept unchanged. This is not so helpful in this case, but it does illustrate what happens pretty clearly. This would be good if I knew what the right threshold value was. Maybe I could separate the coins from the backdrop this way. Or maybe this just isn't the right approach for this particular picture. All right, next we have the 2-0, and in a way, this one I like a lot for this particular example. What's happened is everything over 128 is left alone, everything under 128 is turned to black. And what happens with this is we get a lot more of the detail of the coin. These brighter pixels, we haven't lost some of that detail. So it's easier for us to see it than the original binary one. But it's very similar in that way. And again, the last one should look somewhat similar to our ending point before. The only trick here is anything that's a little bit above 128, anything that's above 128 goes to 0 in this case, and anything under 128 stays unchanged. So we do still have some of the detail of the coins that we might have not had with the binary version. All right, we're going to zoom back into Chrome here for a minute, zoom back into the readings, and I want to take a look at this is just these exact same examples. We want to take a look at things that we can do when we have we're not sure what the threshold should be. So with the earlier examples, I was choosing the threshold every time. That's not always the easiest and most friendly thing to do. So there are 2 algorithms for determining the threshold automatically from the colors, the brightnesses in the image. They're called OTSU and triangle. And they do some complicated things that you don't really need to understand. This is just to show you an option that might be helpful to you. And there's more information about each of these if you're curious about them. So it is fundamentally, it finds a way to pick a threshold that it thinks is most appropriate. I have a code example here, and I also have that over here in PyCharm. I set it up so we're doing binary thresholding, and I used the OTSU algorithm and I used the triangle algorithm. The way that you do that is that you add this extra code to the binary thresh code. Why does that work? ask me another time. But this is what you do. You build a combined threshold description that is literally the sum of these two, and then we are going to pass that to the threshold function. So it'll do both binary thresholding and the OTSU algorithm, or the triangle algorithm. I'm going to switch over to the desktop. So you can see I still have the code running from before. If I hit a key, we'll go on and we'll display first the OTSU. So there it is. You can see there's some more detail of the coins visible, but what's important here is that I didn't really choose 128. It did, or it chose a threshold. So it prints down here at the bottom. It's maybe too small for you to see. This last run, it prints the threshold it determined, which was 161. It's not that different than the threshold I picked, but it's the one that it found to be best. And if I hit a key again, it'll do the triangle, and it picked 105 as a threshold based on the triangle algorithm. One thing you might notice here is there's some speckles off here to the right. It's a little hard to see. It's kind of underneath me. So move it down a little. Those speckles are noise that has shown up just because it picked such a low threshold. There's also another function that was in your notes called adaptiveThreshold. This is doing something more complicated. It's not applying one threshold across the whole image. It's looking within a small patch, lots and lots of little patches, at all the different patches overlapping on the whole image, and it's picking a threshold uniquely for each, with the idea that it wants to just distinguish changes in brightness. So there's a lot of discussion of this in the reading. It's, from my perspective, it's not super critical that you understand this, but I did want to show you the results of the adaptive threshold. So I rewrote the code here. Operating again on the grayscale coin. Oh yeah, I didn't mention this, but notice that all of these have operated on the grayscale image. Most threshold functions do best or require that you provide a grayscale image other than the in-range one and the back projection that we're going to talk about later. I do want to point out one little thing here just so you understand. There's a difference. I'm calling the adaptive threshold twice, and I'm asking it to do thresh binary in both cases. I'm giving it two different adaptations. One of them looks for the average, just straight up average, and the other does a weighted average. And we're going to talk more about Gaussian averaging later. And like I said, this isn't super critical, but I did want to show you that there are these two different approaches that adaptive threshold can do. So I'm going to switch to the desktop. I actually already started running this. So I'm going to put these pictures on top. What I'm doing here in the code is I'm just trying different neighborhood sizes, because as you make the neighborhood size bigger, it looks at more pixels in order to decide what the threshold should be. What you can see is over on the left is the straight up mean, and over on the right is the Gaussian mean. Gaussian mean is a little lighter. The background is a little less noisy, and on the right it's more noisy. But there's especially dark patches at the edges of the coin and the darker coins. So it's doing something. Now we're going to try changing the neighborhood size. So we did and a constant of 2, or now we have a constant of 5. So it's the same neighborhood size, but we changed this constant, and a lot of the noise has gone away. So it's not quite like the binary thresholding, but it's giving us locally binary values in a way that might actually be very helpful to us. And if I just step through here, oof, that's a larger neighborhood and a very low constant, lots of noise, but as I increase the constant, the noise starts to go away. Here I went to a neighborhood of 11 by 11. You might notice that the actual parts of the coins are getting thicker and blockier, which might be a good thing. Makes them easier to detect. We are still getting some noise here. You might have to increase the constant. So here I did a constant of 10 and 11 for the neighborhood size, and that's actually pretty good. The edges of the coins are really clear here. So we're going to pause here. We've talked about several different methods for doing image thresholding with grayscale images. And we're going to wait, and in the next video, we will do some examples of being able to do threshold-like operations on color images instead. So I will see you very soon for that one.